What is today's lecture about? So we'll be talking about communication media. How can we communicate? So now, so far in this course, we've discussed how do we manage networks in terms of performance, transmission time, propagation time, throughput, bandwidth, latency, you know, all these performance metrics that are so important and you need to know them. We also kind of introduce some networking commands that you'll be doing in the lab as well in the tutorial. And we discuss what networking is all about and how can we use them, applications of networking. Now it's time to start talking about protocols of networking. Before we get to the protocols, let's discuss how can we communicate? What are the transmission media options that we have? So we know the topologies, the LANs, the MANs, the WANs, and so on. When we connect them, how do we connect them? Using what kind of transmission media? So today is all about transmission media, different transmission media, their advantages and disadvantages, and to differentiate between their performances. Okay? So I'll be quick. When we talk about the transmission medium, if you remember, one of the major components of communication is the transmission medium. So we have the sender, we have the receiver, we have the protocol, we have a medium in between. So what is that medium? Obviously, it could be wired, it could be wireless, it could be a cable, or it could be without a cable. And if it's without a cable, I'm using wireless technology. Okay, so let's talk about wired and wireless technology. So if you look at transmission media real quick, again, we have many transmission media here. Again, these are the most common. It's either guided or unguided. It's either wired or wireless. So when we talk about wired, we talk about twisted pair, coaxial cable. We call it a coax. Coax could be analog or digital, could be broadband or baseband. Fiber optics, again, like today, you know, good for us. We had the fiber optics team explain to us. So all of you could explain to me now. Maybe I'm going to ask them now when I go to the lecture for them to kind of be involved when I talk about fiber optics. In brief, remember, again, the goal is not to know details, is basically to know a little about a lot when it comes to networking. Okay, so wireless, again, we talk about free space. We'll talk about the different kinds of wireless. We have many, obviously. Again, the most common wireless is what? The most common wireless communication media is what? What do you think?
Radio waves.
Radio waves, yes, yes. Wow, who said that? Bonus point for you. Radio wave, yes. So that's the most common. We'll talk about that. So obviously, we have Wi-Fi, which uses radio waves. You have microwaves as well. So wireless is obviously different spectrums. We'll be talking about this as well. Very nice. So transmission media, simple, guided, unguided, wired, wireless. We have different kinds. Let's go zoom in a little bit into these. So again, performance measure. Let's talk about bandwidth, delay, cost, ease of installation. All these are things that we need to look at when we talk about transmission media. You know, let's start with the first one. Twisted pair. As the name sounds, it's twisted. Twisted pair. You can see my fingers. It's twisted. Why is it twisted? To minimize interference. Because if I put two cables like this, they will interfere with each other. If I twist them, I minimize the interference. That's why we are twisting them. That's something you need to remember. So twisted pair, that's the most common cable. It's two copper wires twisted, again, to reduce interference. It could be either analog or digital. We have distances of several kilometers. You know, we cannot amplify them usually, but typically we are talking about short distances. I don't know if I have a cable here, but twisted pair, you have it in your houses. The cable that you kind of plug to your laptop, that is a twisted pair most likely. Okay, so it looks like a telephone line as well. That's the twisted pair. So distance is very low. You cannot go high distances. Data rates, we're talking about megabits per second. Typically, when you talk about twisted pair, we have minimum shielding. There's not much shield for noise. You have to remember, when you put the cable, we have a shield around it. The whole point of a shield is to minimize noise from the outside. So if there's noise, other signals, they will not interfere with your signal, the thing that you're sending on the cable. Okay, for you to understand. This cable is sending a signal. This signal goes from one end to another. How does it send that signal? We're talking about electrons, you know, electrons, electromagnetic waves, to be more specific. We'll talk about this in a second. So We said the shielding, it is good. It's very cheap. That's why people use it. Obviously, your telephone line, your Ethernet cable is a twisted pair. That's what twisted pair is. How does it look like? This is how it is. You can see you have insulators. They're twisted like this. You have different categories like Cat 3, Cat 5. These are called categories. Okay? Twisted pairs. So you could see 16 megahertz frequency. You don't need to know these. Don't worry about them. But in case you see them, you have different categories. Let's go to the next kind. The next kind is the coax. The coax. You could see we have a copper wire. We have insulating. You can see it has better insulating. It's stiffer because it has better insulating material, better insulation, better protective covers. You know, that's the coax. Who could tell me where do we use the coax? Bonus point. Come on. Where do we use the coax? You should know this. That's easy.
On old desktops and CPUs?
No. TV. Yes, Muhammad. Bonus point for Muhammad.
Okay, fine. That's
of course, TV. You know the cable that has a metal thing in the middle? This thing, and you kind of rotate it in the back of your TV, most likely, before HDMI. So for cable TV, we use the coax. This kind of very stiff cable and has like a metallic thing in the middle. And you kind of rotate it. I'm sure you've seen that before.
It's for the receiver.
Yes, for the receiver as well. And for the TV, 100%. So yes, coax is that. What is it? Still like before, it has two versions, analog and digital. What you could see now, the bandwidth is more. It could go up to 1 gigahertz. You have to remember, twisted pair, we're talking about megahertz. Here we're looking at gigahertz. You have the digital and the analog. One we refer to as the broadband. One we refer to as a baseband. Baseband is digital. Broadband is analog. You could see it has different resistances, better immunity to noise. And you could see now it's fading away. It's kind of dying because fiber optics is taking over. However, coax, many countries still use coaxial cable. Yes, the screw cable, Ibrahim, 100%. Okay, that's what the coax is. This is another connection. We could connect computers together, devices together in a network. Let's move on. Typically, cable TV most likely is using it. Again, broadband, as I said, broadband, we're talking about analog. Typically around 300 megahertz, data rates up to 150 megabits per second. Typically, digital is faster. If you go up to 100 kilometers, you're talking about metropolitan networks, metropolitan cable. We're talking about broadband coax. We could do baseband, use converters in order to transmit digital. You could divide it into different channels, different megahertz channels. So we could use broadband and have channel 1 for something, channel 2, like you have channels on your TV, right? When you're actually going to the TV and you're changing channel, what's happening? That data that's coming to you is divided into different frequencies. You know, let's say MTV on a frequency, CNN on a frequency. This is basically different channels divided into megahertz channel. Each one of them is allocated so that they don't get mixed up, right? So when you're kind of doing your satellite connection, what you're doing is actually looking at the frequency bandwidth that you have. It's coming in and you're dividing it into different frequencies. Not you, the actual cable. It's kind of dividing them into different channels, okay? You could use amplifiers. You could use amplifier to amplify the signal. So if I have a long cable, coax, at one point in time, I'm gonna have an amplifier. If you have like in your country, like cable, you see these people who install cable TV, you would see them coming in and installing amps and repeaters on big poles because they want to repeat the signal so that it kind of arrives to you using coaxial cable. Okay, so you could have different bands. As I said, you could sub-split the cable into different bands or different channels. So this is what you need to know for coax. So now let's upgrade a little bit. Obviously, fiber optics, as the guys were talking about, I don't know if you remember today. So fiber optics is very important because we are using light. We are using the fastest thing on Earth, right? Which is speed of light. So if I could use light instead of signal waves, which are still fast, obviously I could maximize my speed. So the logic behind it is so simple. They said, why don't we get a cable, put inside it glass?
Professor, I cannot hear you. Okay, now I can hear you.
You cannot
Sorry,
hear
you
me?
were muted.
Now I can hear.
Yeah,
No, I think
you were muted.
okay, sorry, fiber optics. Sorry, I don't know what happened. So you can hear me now?
Yeah.
Okay, thank you. So I was saying fiber optics, they came and said speed of light is super fast. How can we use that to send instead of coaxial cable? So the technology is so simple. They said, why don't we create a cable made from glass and send a beam of light on one end so that it reflects on glass until it comes to the other end. This is the basic technology behind fiber optics. So simple. You basically, if you cut a cable, a fiber optics cable, look inside it, you will see glass that kind of prevents the light beams not to go away. So it has to be 100% reflection. It cannot refract. Refract meaning it goes and sneaks out because you lose data. They said, okay, it's easy. Then if basic logic is, if it's a 1, I send light. If it's a 0, I don't send light. So if I want to send 1, 0, 0, 1, it will be light, no light, no light, light in periods. And it's like very similar to Morse code if you think about it. You know, that's the concept of fiber optics. But I'm using light to do that, and it's super fast. So basically, yes, we have a light source, which is sending a pulse of light for 1 bit, a transmission medium, usually very, very thin glass that allows the light to reflect back and forth, almost like in a straight line because the thickness of it is so small. So if you think about, let me just draw a nice picture here. So if I have glass here, I have glass here, I send light here, it's going to reflect back and forth, right? This light is going to reflect back and forth. If I have this glass here and glass here, making sure the index of reflection, you know, it's within. So it's all about the coefficient of reflection and refraction, making sure that these glass material do not allow this light to leave. If it allows it to leave, then you're losing some data, right? So obviously, if I make the distance so small, what does it look like to you? What would it look like if I make the distance between these two pieces of glass so small? What would it look like? The beam of light is moving in a what? The light that I'm sending here will be moving in a what if I make these so small? It will be moving in what?
Zigzag direction.
In a straight line,
Or
not
look.
zigzag. I said if I make the distance small, yes, in a straight line. The first one who said it, bonus point. So it will be looking like the light is moving this way. What you don't know is actually moving in very small because they're so small. Okay? So it's very interesting how these things work. I love it. I don't know if you've seen a fiber optics cable. We could show it to you in the lab. So it's so stiff. It's so stiff. You cannot bend it because inside it there's literally glass. Okay? Very good. So yes, we have a light source on one end, a transmission medium, and you have a detector. The detector is kind of looking, it's like a small camera if you think about it, looking when the light pulses are coming back. Okay? So yes, this is it. You can see you have the index here, the angle. We want to make sure that the index of reflection and refraction are carefully calculated in order to make sure all the light remain within the two pieces or multiple pieces of glass. Okay, so very nice, very nice. I love this. You could see the glasses are very, very thin, so to prevent leakage. So what do we know about fiber optics? There are huge data rates, 1 and more. And I mean, typically 1 is kind of the minimum. So we're talking about 1 gigabit per second and more. I say and more because it could go more than that even easily. It's not affected by power failure. Who could tell me why is it not affected by power failure? Why is fiber optics not affected by power failures?
Because it works with light.
Yeah, and instead of working with what? What do others work with?
Instead of using copper, we use glass.
I know, but why is it not affected by power failure? What does it use? What do we call it? So what do other signals use? I said at the beginning, they use what?
It uses light, not electricity, so it's not affected.
Amplifier.
Exactly. I'm looking for a word. So they use
Amplifier.
what? No. Okay, I'll help you out. Signals, typical signals use electrons. Light uses
Photons?
Photons?
photons. Thank you so much. The first one who said it on the chat.
Yeah.
Bonus point. So yes, So photons, yes, because it's not based on electromagnetic waves anymore. It's based on photons, which is not affected by electricity to start with. So that's the idea behind. So I wanted you to kind of know this. I mentioned it here even. Yeah, sorry. I mentioned it here. You could have seen it here. Okay. It's hard to tap, meaning it's high secure, unlike others where you could tap to it and see. It's very hard to tap. It's thinner than coaxial cable. There are no noise. So there are a lot of advantages. Obviously, we have disadvantages as well. It's difficult to tap. You could see hard to tap. It's good for security purposes. Hard to tap is a good thing. Also, hard to tap is a bad thing because it's not very, very scalable. It's point to point. It's a lot of point to point, you know? So it's not as scalable as others. So I cannot simply cut the cable and connect, you know? It's not that easy. So hard to tap, it's good and bad at the same time. Good for security purposes, bad for scalability and adding elements to the network. Typically, it's one way. It's unidirectional. It's a simplex. So if I wanted to connect A with B, typically I will need a cable like this and a cable like this. You wouldn't see it, but typically it's two cables, one for every direction. Okay? One for every direction. Interesting. Interesting. Okay, let's talk about wireless for a bit. Wireless transmission. So how does wireless transmission work? So the idea of wireless transmission, very similar to normal signals, is based on electromagnetic waves. The idea is so simple. Electrons, when they move, they generate electromagnetic waves. And if I was able to get that electromagnetic wave and broadcast it using an antenna basically listens to the waves. Very simple technology. It's like a speaker, think about it. Speaker produces noise or sound. An antenna, exact same thing. Takes a signal. All it does, it broadcasts that signal. And that signal, in that case, is electromagnetic waves. So are waves. If you go back to Maxwell, back in the days, Maxwell's equation, I don't know if you remember in physics. So we have waves that are emitted, and he was able to figure this out a long time ago. Maxwell's equations kind of figured out we generate electromagnetic waves. When electrons move, they generate waves. These waves is what we are capturing from the cable and connecting an antenna. What you don't know, your phone has an antenna. Everything, a router is an antenna, has an antenna. What is it doing? It's taking the electromagnetic waves from you, capturing it, receiver, and also broadcasting. So it's capturing and broadcasting. Very important. Keep that in your head. If anybody asks you, how does wireless work? Is it magic? No, it's not magic. It's basic principles of physics. I have electrons moving, generating electromagnetic waves that I capture and I broadcast. Okay? So this is the basic logic of wireless transmission, which started in Hawaii initially. So electrons generate electromagnetic waves. Maxwell and Hertz, these are the famous people that kind of figured these electromagnetic waves. Obviously, the number of oscillations per second is what we call frequency. So let me tell you this. Frequency. This is higher frequency. See? 1, 2, 3, 4, 5. This is my frequency. 1 clap per second. For example, I want to make my frequency faster. 3 claps per second. So frequency is how many oscillations per second. That's what we refer to as frequency. Very important for you to know this because we'll do some examples on it. So that's what we refer to as a frequency. So now the distance between the oscillations, 2 consecutive maxima. So a sine wave is usually what the signal is. So this is the distance between 2 maxima or minimum is what we call lambda. Lambda. Okay? Basically the wavelength. The wavelength. How big is your wave? That's what we refer to as the distance between 2 consecutive maxima or minima. And by the way, the wavelength and the frequency have a nice relationship. Let me see if you're clever. Give you a bonus point for sure. What's the relationship between frequency and wavelength?
Frequency is equal to 1 divided by wavelength.
It's not 1. Close enough. I'll show you the equation, but very smart. You're smart, my friend. Yes, they are inversely proportional. Maybe you memorized it, but think about it. If I go fast frequency versus slow frequency, what do you notice? This is frequency high, right? Frequency increases. What happens to wavelength? What happens to wavelength?
It decreases. Decreases.
Decreases. You can see it? And here, frequency. This is slow. Look at it. Slow. What happened to wavelength?
It increases.
Increase. See? If we understand this, we will never forget it. If you memorize the formula, trust me, you will forget. Okay? So it's not typically 1 over F. It's C over F. I'll show you the formula in a second. But you can assume it's 1. C is 1. Okay? So the idea is very simple. Electromagnetic waves are generated, which would result into us capturing it, which would result into us capturing that and broadcasting it. Very nice. I love it. When I talk about this, it gives me goosebumps. You know why? Because you are using Wi-Fi, Bluetooth, all these technology without knowing a lot of what's happening, the basics of it. And now we'll upgrade to talk about the internet and networking. But let's start with the basics, the thing that we use on a daily basis, okay? So again, the antenna could capture it and send it. You have different kind of wireless, from the radio to the microwave to the infrared to visible lights. I'll talk about them. The wider the frequency, as you would expect, if I have a big frequency, I could send more, right? The window's bigger. It's like bandwidth. Bandwidth is frequency. If I give you bigger bandwidth, meaning you can send more. Of course, the wider the frequency, meaning I could send more. So that's something you need to know as well. Again, line of sight technologies are out there where you have to have a line of sight instead of running cables between the buildings. Like in Wollongong, in Knowledge Village, we used to have block 5 and block 15 connected to each other from the roof using, network connectivity. So we have signals, wireless signals, sent from one to the other. Line of sight, they can see each other. It's like a small satellite for local connection. Okay? So yes, as you can see, the relationship is lambda F equals C. So basically F equals C over lambda. So yes, they are inversely proportional, of course. Again, where C is the speed of light. C is the speed of light, okay? C is the speed of light. So that's a basic idea. You could derive this. This is, if you derive this, you get this. So but focus on lambda F equal to C. So we have different electromagnetic spectrum. This is what we call the electromagnetic spectrum. Very nice. I love this. Electromagnetic spectrum is basically different frequencies that we have. So we said we have something called the frequency. The wider the frequency is, the more I can send. Obviously, it has its other issues as well. Let's look at this. So we have radio waves, microwaves. Radio waves, as you can see, we're talking about low frequency LF, MF, medium frequency, HF, high frequency. You know, like in your radio, you have AM and you have FM. You all know that, right? So amplitude modulation and frequency modulation. So you have different frequencies. Also, you have TV, you have VHF, UHF, SHF. Anybody knows what they stand for? What is VHF? This was high frequency. What is this? Very high frequency. What do you think UHF is?
Ultra high frequency.
Ultra high frequency. What do you think SHF is?
Super high frequency.
Super. E?
Extreme.
Extreme. D?
I have no idea.
You got most of it. You can Google this and see. But you can see, obviously, these are all high frequencies. They started with one. And then they went up and added all this. But the logic is simple. Radio waves have limited frequencies between 10 to the power 4 hertz, and 10 to the power 8. Microwaves, you could see the frequency is increasing. So when I'm going like this, the frequency is increasing. You can see, for example, X-ray. X-ray, very high, huh? You see? This is X-ray. You have gamma rays, you know? So these are all we're sending at a specific frequency. Infrared, like your remote control, right? Infrared, your TV remote control. You're using infrared. We're using it at this specific frequency. Microwaves like satellites also. So you can see different signals have an electromagnetic spectrum. So if I'm generating an electromagnetic wave, I'm generating it at a specific frequency. You know? And if I'm generating it at a specific frequency, therefore, that gives me specific limitations. So they called it names. These guys called them names. You could have called, instead of microwave, call it something else. But these are kind of the names that work at these specific frequency. Okay? So yes, Isa, infrared is indeed works at a high frequency. You could send a lot with it. But the problem with it is line of sight. It's not omnidirectional. It's line of sight. It has to have line of sight. So if you have something in between, it gets obstructed. Okay? So let's watch a small video. You know, I'm going to share with you something, a quick tutorial, a 5-minute tutorial on wireless communication. And then we'll finish up the lecture. Okay? We share. We'll talk about cellular communication and others later on. Of course, they use radio waves. They use radio waves like everything else. So let's watch this video real quick to give you an idea.
How many of you really understand what goes on when you text your friend across the ocean and they get the ping almost instantaneously? Allow me to entertain you with a little thought experiment. When you press send on your favorite messaging app, where's your message really going? Into the air, you'd say, like radio waves. But let's back up a bit. When you press send on a messaging app such as WhatsApp, you're essentially sending instructions to your mobile processor via tiny copper wires on a printed circuit board inside your smartphone. Now, these instructions are essentially electrical impulses, right? And electrical impulses are just electrons flowing along the potential difference. How exactly does your message jump into thin air from being electron flows and copper wires? At one stage, you had a circuit board that you could touch and feel and even smell. And then suddenly you have radio waves in the invisible part of the spectrum, flying away into thin air at incredible speeds. What's in between? Well, an odd-looking device. It's an antenna, which roughly translates to a pole in Latin. An antenna is a metal-tongued voodoo device that swallows electrical impulses and spits out radio waves. It's as silent as the dead, but its screams can be heard for miles. Specifically, a Wi-Fi antenna like the one here in the picture screams at 2.4 gigahertz, that's more than 2 billion beats per second, and spits out waves of roughly 12.5 centimeters in length. Unlike visible light, these waves can pass through certain materials and even bend around corners. But how does an antenna produce radio waves? Before we answer this question, let's take a small detour. Do you remember the reason buzz in pop science about gravitational waves? They're basically fluctuations in gravitational field propagating as radiant energy. Einstein's general relativity predicted their existence many years ago, and we've only recently discovered them. Just like gravitational waves, electromagnetic waves are fluctuations in an electromagnetic field, propagating as radiant energy. And, not much unlike the story of gravitational waves, the existence of invisible electromagnetic waves was predicted by Maxwell's equation well before their discovery by Heinrich Hertz. So, to produce radio waves, you need to create fluctuations in the electromagnetic field. And to create those fluctuations, you need electrons moving around in a conductor. The act of radio wave synthesis is a carefully choreographed rhythmic dance of electrons and tiny copper wires. Like perturbations in still water that radiate outward from the point of disturbance, the electron flows in an antenna cause perturbations in the electromagnetic field, which radiates out into space as electromagnetic waves. When you press send on your favorite messaging app, your mobile operating system sets off a chain of events that ultimately encodes the message as a carefully choreographed electron dance. This dance results in rhythmic ebbs and flows in the electromagnetic field in the surrounding space, which radiates outwards towards a cell tower. The receiving antenna on the cell tower feels these ebbs and flows on its conducting surface, inducing an electron dance very similar to the one from the transmitter. This electron dance is again a set of electric impulses in tiny copper wires, which are decoded by the hardware at the cell tower. The decoded information is then carried on high-throughput cables for thousands of miles across countries, continents, and even oceans, through transatlantic communication cables or some other submarine communication cables, to a cell tower near your friend across the ocean. From the tower to your friend's phone is another wireless jump, and finally, your friend hears the familiar ping. How does the phone know where the cell tower is? It doesn't, and it doesn't need to. Your phone broadcasts your message in all directions for anyone to listen to. But don't worry, your message will be encrypted, and only the cell tower can decode your message.
Okay, that was interesting. So I wanted a simple way for you guys to see how wireless works. That's fun, no? It's interesting how the whole mechanism, in a simple way, of course, but still now you understand the whole movement of electrons is in a conductor, obviously like copper, is the one generating electromagnetic waves around it, and that movement is so specific to what is being sent and therefore received, encrypted until we get to the end, okay? So this is interesting. We'll watch later on how the internet works with the open protocols and everything, but keep in mind the physics behind it is so important. The physics is what led to all the technologies that we see around us, okay? Do you want me to talk in the same tone like the guy in the video? You know, that would be funny. Okay. Yes, yes. Connected to the same Wi-Fi as you. Doesn't depend what kind of network are you using, Isa. If you're using the internet protocol, of course, it's going to go to a tower and come back to them. If you're using IP, internet protocol. If you're using a LAN, a local area network, of course not. Then it's going to go to them immediately. If you're doing it within the LAN. So the antenna, the tower is not needed anymore, because the router will do all the magic, depending on what kind of protocol are you using. So that's what something we'll be talking about the next 5 weeks. Protocol. You're going to learn a lot of protocols, and you'll understand what the protocol means. If you go back to the basic of communication, we have sender, receiver, and a medium. So we are still here in the medium. Now, the next step will be what is the protocol and how to use it and what kind of protocol levels do we have. How does it know? Based on the ID. Part of the message, there is a sender and receiver. So every user has an ID, typically your IP. Your IP is unique to you, and that uniqueness is what defines who you are connected to a network. So the IP address is super important. We talked a little bit about it when we pinged. When you were pinging, that's your ID, and that's what is part of the message. These electrons, part of them, when we say, I mean, let's understand. When we said we're sending a message, my name is Muhammad. You know, I could type it on the chat. My name is Muhammad. This is changed to zeros and ones. A lot of you think, oh, we're sending zeros and ones. Of course not. We're not sending 0 and 1. What we're sending are electromagnetic waves, basically electrons moving in a very perfect motion, you know, and that is what defines your message. Interesting. I like it. I like it a lot. So let's move on. Let's continue the lecture. Okay, so we said back to maybe continue where the guy stopped. Again, electromagnetic waves have different frequencies, which define how much we can send, what kind of technology. Very important. You need to know this, guys. You need to know this, huh? So you can see satellites are in this range, in 10 to the power 9 range. So you can see because they use microwave, satellite typically uses microwaves. Again, fiber optics, you could see in a high range. Again, one more time, higher frequency means I could send more. Keep that in your head, okay? You can see twisted pair are on the low end of the spectrum. Twisted pair are at the low end of the spectrum, okay? The coax is somewhere here. Okay, so let's look at the frequency. How do you get the frequency? So who gets the frequency and how? Obviously, you have some federal commission, which is the Federal Communication Commission. We call it the FCC. These are the ones who allocate frequencies. For example, if I want to create a new technology, a new drone, you know, I need to know what frequency I could operate in so that it doesn't interfere with others, right? You all know why we have to turn off our phones in the airplane when it's landing or taking off. Why do we have to turn off our phones?
So that it doesn't interrupt the frequencies that
what
are used to
frequency?
communicate
Yeah, the frequencies they're using to communicate with the airport, right?
with the plane.
So
Yeah.
it might interfere because it depends on what frequency spectrum are you using. So typically it's 2.4 gigahertz. It depends on what model. Again, if you look at Wi-Fi, which is 802.11 ABCD, you can see that they work at specific frequency. And this is the frequency that you're allowed to use in order to send data or receive data. Therefore, it doesn't interfere with other frequencies. Okay? So yes, most transmissions typically use a narrow frequency. Why? Because why do we use a narrow frequency, not a wide frequency? Why would we use narrow versus wide? Because for narrow frequencies, it will not basically interfere with others, you know, because it's so narrow. So my frequencies are only for me. If I have a wider frequency, it might overlap. You could see like it's kind of over like noise from other signals. Okay, so spread spectrum is something we call, you could hop from one frequency to another. So you don't use the same frequency all the time. You have a pattern of jumping. So the signal will use this frequency now and then hop to another frequency. So this is good for security. We call it a spread spectrum, which means that I don't have to use the same exact frequency. I will be jumping from one frequency to another. Okay? You can still hear me, huh? Can you hear me, guys?
Yes, Professor.
Yeah. Okay, thank you so much. So let's talk about some of these wireless technologies: radio wave, microwave, and infrared. So radio waves are easy to generate because most technologies use radio wave. They could travel long distances. They could penetrate buildings. They're omnidirectional, which means they are in all directions. Okay, omnidirectional. They're not directional, like infrared, for example. They're frequency dependent. Low frequencies, they follow the ground and pass through obstacles. At high frequencies, they typically travel in straight lines and bounce off obstacles. So who uses high frequency? Who could give me an example about how high frequencies, they actually bounce off walls? Who could give me an example? High frequency bouncing off walls. What uses radio waves at high frequencies? Come on, yalla.
Microwaves?
Satellite.
Satellite, okay.
Yeah. Satellite uses a form of radio frequencies or microwaves even. So it's high frequency. What do you notice when you're watching TV and it's raining outside? What do you notice?
It's buffering
What's that?
sometimes. It's buffering. The TV buffers a lot.
Because we have a poor signal, right? Why? Because the signal is being absorbed by rain, you know? That's the idea, basic idea. Radio waves even. You see the connection goes bad when we have bad weather condition. Because if I'm working at a high frequency, obviously if I'm working at low frequency, that should be easier. So microwave is typically like an upgrade of radio waves. So as you see, it travels in a straight line because it's a high frequency radio wave, if you think about it. It's blocked by walls, absorbed by rain. It's inexpensive to build a microwave communication network. Typically phones, garage doors, most of these are using microwaves to send and receive. Again, weather interference, easy taps. Signals could be bounced off structures, as I said, because they become out of phase. So microwave, as I said, think about it as an upgrade to radio waves, but with higher frequencies. Satellite, again, an upgrade to microwaves. But if you think about it, satellites use radio waves, but at a very high frequency. And what you need to know that the satellite always stays constant relative to the ground station. So if I have a ground station, this dish that you have, what's happening? This dish relative to the satellite is constant. Okay, they're relative to each other. That's why you have that dish that allows it not to miss the actual straight line communication between them. It's very interesting. You have to remember, satellite is moving, right? How does it stay constant? Who could tell me? Come on, basic information here. The satellite is moving, of course, up there. But I'm telling you, it stays constant relative to the ground station. How come? Because what? What else is moving?
Because the satellite is also moving.
No, I know the satellite is moving, but your
Oh, you said the satellite is moving.
The Earth is moving.
The Earth is
Earth
also
moving.
moving.
Thank you so much. Because Earth is moving, and they're moving relative to each other, they remain constant. You get it? So that's the logic behind it. In case you're wondering, how on Earth? Imagine if the satellite moves, I have to go and move my dish in my rooftop in order to cast a signal, right? Obviously, it doesn't make sense. So you can see these are simple things. We call it geostationary Earth orbit. They're orbiting around the Earth. They're limited in number, typically in the range of 200, 180, because obviously we don't want them to interfere with each other and start hitting each other. Okay, think about it as a big microwave repeater out there rebroadcasting your signal. Okay, that's what you do with GPS and everything. So microwaves are used for unicast. Again, cellular, telephones, and so on uses radio waves or microwaves to be specific. LANs, Wi-Fi, all these are using microwave technologies. Okay, infrared, it's a line of sight. The wavelength becomes shorter because the frequency becomes higher. You have high frequency, hence very short wavelength. Very short wavelength, meaning I cannot go through obstacles, right? So they're relatively cheap. And again, we use it in remote controls in your TV. If you change the TV channel, if you look at it, you cannot see it with your eyes because infrared are invisible to a naked eye. If you put your camera on top of your TV in remote control, you would see that when you push on it, there is a light. There is a light showing, but you cannot see it, right? So infrared is very simple technology, has been there for ages. The good thing about it's very cheap, and again, high frequency, but the bad thing is it doesn't go through walls, so you have to have line of sight, okay? So this is kind of my part of the lecture.